In this video, I'm going to go through equations of planes in R3. So for an example, suppose we have a general equation for a plane x plus y plus 2z equals 1. So the normal vector to that plane, we can just pull off the coefficients in front of x and y and z. So 1's in front of x, 1's in front of y, and 2 is in front of z. So 1, 1, 2 is the normal vector. And then for the normal form, it's similar to a line in R2. We have n dot product x equals n dot product p. So we need a point P on the plane. So in this case, we've got a fairly simple equation here. If I just set x equal to 1 and y equal to 0 and z equal to 0, we would be on the plane. And so the normal form of the equation here is going to be 1, 1, 2 dot product with the x vector, x, y, z. That's equal to 1, 1, 2 dot product p in vector form 1, 0, 0. And just check that that's correct. On the left hand side we've got x plus y plus 2z, and on the right hand side we've got 1 plus 0 plus 0. So sure enough, we're back to the general equation here. What about the vector form? So we could imagine the equation, the plane looking say like this in a very general representation. We've got our point P, we've got our normal vector to the plane, and then if we pick two more points Q and R in the plane, and the vector U is Q minus P and the vector V is R minus P, as long as U and V are not parallel, then we can put those into the vector form of the equation like this: x equals the point P plus a scalar s times u plus another scalar t times v. So all we have to do is find 2 points Q and R in the plane so that we'll get two non-parallel vectors u and v. So let's do that. We could pick, for example, Q. If we set x equal to 0, y equal to 1, and z equal to 0, we would be on this plane. And for point R, we could pick, say, 0, minus 1, 1. That will also be on the plane. It's somewhat arbitrary how we pick P and Q and R, but as we discussed in the video on equations of a line in R2, it doesn't really matter. We're often picking these points for convenience to make the equations as straightforward as possible. So in this case, let's figure out what u is equal to. So u is q minus p. So if we look at elements in q and elements in p and subtract them, we're going to have q is 0, 1, 0, and p is 1, 0, 0. So q minus p, which is going to give us our u vector, is going to be minus 1 and 1 and 0. And for the v vector, our point R is 0, minus 1, 1, and p is 1, 0, 0. So v is going to be minus 1, minus 1, 1. So our vector form is going to be x equal p plus su plus tv. So the x vector is x, y, z. Point P in vector form is 1, 0, 0, and plus s times vector u, which is minus 1, 1, 0, plus t times vector v, which is minus 1, minus 1, 1. And if we break that out into the components, we'll get the parametric equations x equals 1 minus s minus t, y equals 0 plus s minus t, and z equals t. So those are the parametric equations corresponding to the general equation x plus y plus 2z equals 1. And we could just double check that. If I add x plus y plus 2z according to these parametric equations, then the general equation tells us that we ought to get just a constant 1 when we do that. So I'm going to have 1 minus s minus t, add on s minus t, so we're going to have 1 minus 2t, and then add on 2z, so we're going to have 1 minus 2t plus 2t, so all the t's will cancel, we'll be left with just the constant 1, which is what we wanted.